Welcome back to AI Academy. Today we are going to start new course which is on natural language processing with transformers. Since this is the first course, we will start with the basic introduction about NLP and transformers with HuggingFace. This course is dedicated to providing you with a solid foundation in transformer architecture, its history, key components, and the transformative impact it has had in the field of NLP. By the end of this course, you'll have a good grasp of how transformers work and be ready to dive deeper into the HuggingFace Transformers library. Okay, so what is transformer? The transformers have revolutionized NLP by providing a powerful and flexible model architecture that has outperformed previous models on many tasks. Introduced in the seminal paper, Attention is All You Need by Vaswani, the transformer model discards the recurrence found in traditional models like RNNs and instead relies entirely on a mechanism known as self-attention. The key characteristics of transformer architecture are the encoder-decoder framework, which consists of two main components, the encoder and the decoder. The encoder converts an input sequence of tokens into a sequence of continuous representations. And the decoder takes the output of the encoder and generates an output sequence, one token at a time. The self-attention mechanism allows the model to weigh the importance of different tokens in the input sequence, enabling it to capture long-range dependencies more effectively than RNNs. Since transformers do not inherently capture the order of tokens, positional encodings are added to the input embeddings to provide information about the token positions in the sequence. The parallelization. Unlike RNNs, transformers allow for much greater parallelization, making training more efficient. Let us now discuss about history and evolution of transformers in NLP. So, before transformers, NLP models were primarily based on recurrent neural networks, RNNs, and convolutional neural networks, CNNs. While these models achieved significant milestones, but they had limitations in handling long-range dependencies and parallelization. The RNNs and LSTMs introduced the concept of sequential processing, but struggled with long-term dependencies due to gradient vanishing and exploding problems. The attention mechanisms enhanced RNNs by allowing the model to focus on different parts of the input sequence, but were still constrained by sequential processing. And the transformers introduced by Vaswani in 2017 eliminated the recurrence by relying entirely on self-attention mechanisms, thus enabling better handling of long-range dependencies and parallelization. The impact of transformers on NLP are that transformers have set new state-of-the-art results across a wide range of NLP tasks, including machine translation, text classification, and language modeling. Notable models based on transformer architecture include BERT, short form of bidirectional encoder representations from transformers, which utilizes a bidirectional approach to pre-training, capturing context from both directions. The GPT, called as generative pre-trained transformer, focuses on autoregressive language modeling, generating coherent text by predicting the next word in a sequence. And the T5, short form of text-to-text transfer transformer, frames all NLP tasks as a text-to-text problem, simplifying the process of applying the model to different tasks. Let us now talk about the key concepts of the transformer. The first one is the self-attention mechanism. At the heart of the transformer is the self-attention mechanism, which allows the model to weigh the importance of different words in a sentence when encoding or decoding sequences. This mechanism captures the dependencies between words regardless of their distance in the sequence, making it highly effective for understanding the context. Next is encoder-decoder architecture. The original transformer model consists of an encoder and a decoder. The encoder reads the input sequence and transforms it into a set of continuous representations. It is composed of multiple layers, each containing two sublayers, a multi-head self-attention mechanism and a position-wise fully connected feed-forward network. The decoder generates the output sequence. Like the encoder, it is composed of multiple layers. Each layer has three sublayers, a multi-head self-attention mechanism, an encoder-decoder attention mechanism, and a position-wise fully connected feed-forward network. The encoder-decoder attention mechanism allows the decoder to focus on relevant parts of the input sequence during generation. Another one is positional encoding. Since transformers do not inherently understand the order of the sequence, positional encodings are added to the input embeddings to provide information about the relative positions of the tokens in the sequence. And in the last, the multi-head attention. This mechanism allows the model to focus on different parts of the input sequence simultaneously, providing multiple attention scores for each token. It improves the ability of the model to capture various aspects of the relationships between words. The detailed components of the transformers are attention mechanisms. The attention mechanisms are crucial for the functionality of transformers. They allow the model to dynamically focus on different parts of the input sequence. The self-attention mechanism computes a representation of each token by considering the entire sequence using three main matrices: query, key, and value. Next is the feed-forward networks. These are applied independently to each position in the sequence. They consist of two linear transformations with a ReLU activation in between, allowing the model to learn complex transformations of the input features. And the layer normalization, it is applied to each sublayer. It stabilizes and accelerates the training process by normalizing the input across the features for each layer. The advantages of transformers are like parallelization. Unlike RNNs, which process tokens sequentially, transformers can process tokens in parallel, significantly speeding up training and inference. The long-range dependencies. Transformers can effectively capture long-range dependencies in sequences, which is a limitation in traditional RNNs and LSTMs. And the scalability. Transformers scale well with large datasets and models, enabling them to learn from vast amounts of data and improve their performance on various tasks. The real-world applications of transformers are but not limited to language translation, the initial application of transformers, where they significantly improved the quality and efficiency of machine translation systems. Text summarization, generating concise summaries of longer texts. Question answering, providing precise answers to questions based on input text. Text generation, creating coherent and contextually relevant text based on given prompts. Basically, transformers have transformed the field of NLP by providing a flexible, scalable, and highly effective architecture for various language tasks. Their ability to capture complex dependencies and process data in parallel makes them a cornerstone of modern NLP research and applications. The HuggingFace Transformers library has further democratized access to these powerful models, allowing practitioners to easily leverage them for a wide range of tasks. Let us now talk about the overview of HuggingFace Transformers library and ecosystem. The HuggingFace has developed a comprehensive ecosystem that simplifies the use of transformer models in natural language processing, NLP. This ecosystem includes several powerful tools and libraries designed to make it easier for researchers and developers to access, fine-tune, and deploy state-of-the-art models for a wide range of NLP tasks. The HuggingFace Transformers library is the centerpiece of the ecosystem. It provides an easy-to-use interface for accessing a variety of pre-trained transformer models and fine-tuning them on custom datasets. Here are some key features of the library. Model Hub is a vast repository of pre-trained models covering a wide range of NLP tasks. Users can easily search, download, and integrate these models into their applications. The Model Hub supports multiple model architectures, such as BERT, GPT-2, Roberta, T5, and many others. The tokenizers are the library offers efficient and versatile tokenizers that support various tokenization strategies. Tokenization is the process of converting text into numerical tokens that the models can process. HuggingFace provides tokenizers for word, subword, and character tokenization, which are optimized for speed and compatibility with different model architectures. The Trainer API is a high-level interface that simplifies the process of training and evaluating models. The Trainer API abstracts away much of the boilerplate code required for training models, allowing users to focus on their specific tasks. It supports features such as distributed training, mixed precision, and hyperparameter tuning. Let us talk about HuggingFace Model Hub in detail. The Model Hub is an integral part of the HuggingFace ecosystem. It hosts thousands of pre-trained models that can be used for various NLP tasks such as text classification, named entity recognition, question answering, text generation, and more. The Model Hub offers the following features: search and filter. Users can search for models based on specific criteria such as task, architecture, dataset, language, and more. This makes it easy to find the most suitable model for a particular use case. Community contributions. The Model Hub encourages contributions from the community. Researchers and developers can upload their pre-trained models, making them available to others. This collaborative approach fosters innovation and accelerates the adoption of new techniques. Documentation and examples. Each model on the Model Hub comes with detailed documentation and usage examples, which help users understand how to effectively utilize the models in their projects. In addition to the Transformers library, HuggingFace provides several other libraries that enhance the overall ecosystem, such as Datasets. Library offers a seamless way to access and preprocess datasets. It integrates with popular frameworks like Pandas and NumPy, making it easy to manipulate and transform data. The Datasets library supports a wide range of datasets and includes tools for data loading, preprocessing, and augmentation. Accelerate. The Accelerate library provides tools for optimizing the training process. It includes features such as distributed training, mixed precision training, and gradient accumulation, which help to speed up training and reduce resource usage. Accelerate is designed to work seamlessly with the Transformers library, allowing users to scale their training workflows efficiently. Diverse model selection. The Model Hub includes models trained on various tasks such as language translation, summarization, text generation, and more. Users can find models tailored to specific languages, domains, or datasets. Versioning and updates. Models on the Hub are versioned, ensuring that users can access previous versions if needed. Authors of models can update their models and provide release notes, making it clear what changes or improvements have been made. Integration with Transformers library. The models from the Hub can be easily loaded using the Transformers library. This integration simplifies the process of deploying pre-trained models in applications. Let us now look into some of the example usage. In the first example, we will be doing a sentiment analysis from the sample text. For that first, we're importing a function called pipeline from the Transformers library. The pipeline function is like a Swiss Army knife for NLP tasks. It can help us set up models for various tasks like sentiment analysis, text generation, translation, and more, all with just a few lines of code. Next, we need to specify which model we want to use for our task. The HuggingFace Model Hub has thousands of pre-trained models, and here, we're choosing one called Distilbert, Base, Uncast, Fine-Tuned, SST2 English. This model is a streamlined version of BERT, specifically fine-tuned for sentiment analysis on English text. Now, we create a sentiment analysis pipeline by passing the task name, sentiment analysis, and the specific model's name to the pipeline function. Think of this step as setting up our tool with the right attachments for the job. With our classifier ready, we can now use it to analyze the sentiment of any given text. In this case, we're feeding it the sentence, "I love using HuggingFace transformers." The classifier processes this sentence and determines whether the sentiment expressed is positive, negative, or neutral. Finally, we print out the result, which will tell us the sentiment of our sentence. If the model thinks the sentence is positive, it will say so, and if it's negative, it will say that instead. This tells us that the model is almost certain, 99.98% sure, that the sentiment of our sentence is positive. And that's it. With just a few lines of code, we've leveraged a powerful pre-trained model to perform sentiment analysis, thanks to the HuggingFace Transformers library. Cool, right? Let us now talk about the tokenizers. tokenization is a crucial step in preparing text data for input into transformer models. The HuggingFace Tokenizers library provides efficient and flexible tokenization methods. Key features include: fast and efficient tokenizers are written in Rust and provide bindings for Python, ensuring they are both fast and efficient. This is particularly important when dealing with large datasets. And the support for multiple tokenization strategies. The library supports various tokenization methods, including byte pair encoding, word piece, and sentence piece. This flexibility allows users to choose the best method for their specific use case. Also, the custom tokenization with which users can create custom tokenizers tailored to their specific needs, such as adding special tokens or modifying tokenization rules. Let us now look into the example usage of tokenization. First, we import the BERT Tokenizer class from the Transformers library. The BERT Tokenizer is responsible for converting text into a format that the BERT model can understand, which involves breaking down sentences into tokens and then mapping those tokens to numerical IDs. Next, we load a pre-trained tokenizer for the BERT model. Specifically, we're using the BERT base uncast version. Uncast means that the tokenizer will convert all characters to lowercase before tokenizing, ignoring case differences. Now, we use the tokenizer to process an input sentence. The tokenizer method converts the input text, "Hello, how are you?" into a format suitable for the BERT model. By setting return_tensors equals pt, we tell the tokenizer to return the output as PyTorch tensors. Finally, we print the tokenized output. The output is a dictionary with 3 keys: input_IDs, token_type_IDs, and attention_mask. Here's what each of these means. Input_IDs, this is a tensor containing the token IDs for our input text. Each token in the input sentence is mapped to a unique ID based on the BERT vocabulary. The special tokens, CLS, with ID 101, and SEP, with ID 102, are added at the beginning and end of the input, respectively. These tokens are used by BERT to understand the boundaries of the input sequence. The actual token IDs for "Hello, how are you?" are 7592, 1010, 2129, 2024, 2017, 1029. Combined, the input_IDs tensor looks like this: tensor 101, 7592, 1010, 2129, 2024, 2017, 1029, 102. Token_type_IDs. This tensor is used to distinguish between different sequences in tasks like question answering or sentence pair classification. Since we only have one sequence here, all the values are 0. The token_type_IDs tensor looks like this: tensor 0, 0, 0, 0, 0, 0, 0, 0. Attention_mask. This tensor indicates which tokens should be attended to, with a value of 1, and which are padding, with a value of 0. In this case, all tokens are part of the actual input, so all values are 1. The attention_mask tensor looks like this: tensor 1, 1, 1, 1, 1, 1, 1, 1. Summary. Input_IDs, tensor 101, 7592, 1010, 2129, 2024, 2017, 1029, 102. These are the token IDs for the input text, including special tokens, CLS, and SEP. Token_type_IDs, tensor 0. Indicates that all tokens belong to the same sequence. Attention_mask, tensor 1. Indicates that all tokens should be attended to. By understanding this output, you can see how text is transformed into a numerical format that the BERT model can process. This transformation is crucial for allowing the model to perform tasks like classification, translation, and more. Let us now talk about the Trainer API. The the Trainer API in the Transformers library provides a high-level abstraction for training and evaluating models. It simplifies the training process by handling common tasks such as data loading, optimization, and evaluation. Key features include ease of use. The Trainer API reduces the amount of code needed to set up and train models, making it accessible to users with varying levels of expertise. Advanced features. The API supports advanced training features such as distributed training across multiple GPUs, mixed precision training for faster computation, and hyperparameter tuning. Flexible configuration. The users can customize various aspects of the training process, including learning rates, batch sizes, and evaluation metrics. Let us now look into the example usage of classifying movie reviews. So, first we import necessary components from the Transformers library, PyTorch, and the dataset utilities. Then we define a custom dataset class that inherits from PyTorch's dataset. This class includes init, initializes the dataset with the data. Len, returns the length of the dataset. getItem, retrieves an item by index. Next, we create lists of dictionaries representing our training and evaluation data. Each dictionary contains input_IDs, the tokenized input IDs. Attention_mask, a mask to indicate which tokens should be attended to. Labels, the label for the input. Then, we wrap our data lists in the custom dataset class. Next, we define the training configuration, specifying where to save the results, how many epochs to train for, the batch size, evaluation strategy, and disabling reporting warnings. Then we load a pre-trained BERT model for sequence classification. Next, we create a trainer instance, passing in the model, training arguments, datasets, and a custom optimizer, AtomW from PyTorch. And in last we start the training process. Here's what each part of the output means. Global_step equals 3, this indicates that the training process has completed 3 steps. Given our small dataset and the training configuration, this means the model has processed the entire dataset for each epoch, totaling 3 epochs. Training_loss equals 0.35, this is the average training loss after completing the training. A lower loss generally indicates better performance, though this is highly dependent on the specific task and dataset. Metrics, this is a dictionary containing various metrics related to the training process. Train_runtime equals 8.05, the total time, in seconds, taken for training. Train_samples_per_second equals 0.372, the number of training samples processed per second. Train_steps_per_second equals 0.372, the number of training steps processed per second. Total_floss equals 12333330720, the total floating point operations, flops, performed during training. This is a measure of computational complexity. Train_loss equals 0.35, the training loss, same as mentioned above. Epoch equals 3.0, indicates that training was performed for 3 epochs. So, this code demonstrates how to set up and train a BERT model for a sequence classification task using the HuggingFace Trainer API. The output provides insights into the training process, including the number of steps completed, training loss, runtime, and other metrics. By using the Trainer API, you can streamline the training process, making it easier to manage and analyze your machine learning experiments. The HuggingFace Transformers library and its associated ecosystem provide a powerful and user-friendly platform for leveraging state-of-the-art NLP models. Whether you are a researcher, developer, or data scientist, these tools can help you quickly integrate advanced NLP capabilities into your applications. By providing pre-trained models, efficient tokenizers, and high-level training APIs, HuggingFace simplifies the process of working with transformers, making cutting-edge NLP accessible to a broader audience. In this lecture we have provided a comprehensive introduction to the transformer architecture, its evolution, and the HuggingFace ecosystem. By implementing a basic transformer model and exploring the HuggingFace Model Hub, you've taken the first steps in leveraging these powerful tools for your NLP projects. In the next chapters, we'll delve deeper into specific applications and advanced techniques to further enhance your understanding and skills. In the next lecture, we will cover the topic of text classification. The text classification is one of the most common tasks in NLP. It can be used for a broad range of applications, such as tagging customer feedback into categories or routing support tickets according to their language. Thank you for joining us for this lecture. We hope you found the content informative and helpful. If you have enjoyed this video, please give it a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more educational videos. Your support helps us create more valuable content for you. See you in the next video.